as the recording started. There we go. Okay, so over to you then if you want to give your presentation. Thank you. Oh, and if anybody has any questions, drop them in the chat and we'll pick those up at the end. Thank you.
Lovely. Well, thank you very much. Thank you for having us as well to talk to you this presentation. Alex, if you can go to the next slide, please. So there's a few things that we're going to run through and talk in today's presentation. As mentioned, this is a case study using the Hill House sidings area as part of TRU as an example on how we've approached the legacy mine working issues in that area. So we're going to briefly talk through background to TRU, the Hill House siding site, and what the history of mine workings has been at Hill House. We're going to talk through the GI that has been undertaken and ultimately how we've gone through and done our mine working treatment design. Alex and Anjana are then going to run through the probing and grouting that has been undertaken, how we've verified verified the treatment through testing, and then provide a bit of a wider context of the grouting works that have been undertaken as part of the TRU project. So just to introduce ourselves, my name's Claire Bennett. I'm a Grand Engineering Associate with Arup, and I was also the Hill House Sidings Geotechnical CRE.
Good afternoon, everyone. My name's Alex Wilding. I'm a Senior Geotechnical Engineer with BAM Ritchie's, currently working on TRU mine infill projects that we still have going on. Yeah, Anjana.
Hi everyone, I'm Anjana Gopan. I'm a geotechnical engineer working with BAM Ritchie's. Been working in TRU mine infill works from November 2023. Yeah, that's me.
Thanks, Anjana. I'm not going to spend too much time talking through the TRU project, as I'm sure a number of people on this call are familiar with it. But essentially, it's upgrading the rail network between Manchester, Victoria through to York via Huddersfield and Leeds. That's 70 miles of upgrades to this area of works, which includes a number of stations, upgrades and improvements, as well as significant civils works, rail systems improvements, and works through the tunnels that exist along this area of the route. Ultimately, this is aimed at speeding up journey time between Manchester and York, promoting greener travel through electrification, and just ensuring that there's a more frequent and reliable train service for this extent. In terms of the Hill House Sidings site, Hill House Sidings is located just to the north of Huddersfield. So as you come out of the Huddersfield station towards Dainton Station, Hill House Sidings is, you can see it on the left-hand side. It's a former parcel of land that was a railway sidings and it's in Network Rail's ownership. Alex, can you use the next slide, please? Thank you. So when we started the works at Hill House, the site looked like the image on the left-hand side. It was occupied by a number of individual leases with various industrial units. As I mentioned, the site has historically been a sidings. So the image on the right-hand side here is taken from RAF imagery in the 1940s, and you can see the number of different railway lines coming from the main line into the site there. In terms of the proposals and what the works at Hill House comprised, this is taken from our GA drawing. What we have is a new reception road, which is coming off from the main line. That's the bottom left of that image. That comes into the siding site then and splits into 4 individual sidings, which is the kind of bulk of the red linear lines that you can see on the right-hand side there. In addition to the 4 sidings, there's also a new MMT siding, and those are looking at servicing the new trains along this area of the route. Additionally, there's an access road coming in from Alder Street and wrapping around the top of the buffer stops, and new top facilities supporting the maintenance and the operation of the sidings. The access road itself then goes down back to the main line, wraps around the new sidings themselves to form a new access point onto the mainline site. Thank you, Alex. It's useful at this point just to provide a little bit more context about the approach to managing mining from a Network Rail perspective, and particularly drawing reference to the Network Rail mining manual that is available and the projects are delivered in line with. Particularly the module that's of most relevance with respect to what we're talking around today is module 5, which is managing the risk of mining from a design and construction perspective. And that module details the stages that should be followed on a project to ensure that the mining risk is appropriately considered and mitigated. So that starts through GRIP 2 and 3 with the production of mining reports, which are produced by the PME, so the principal mining engineer, which highlights the potential for mining works beneath the site. And that's taken forward then by the designer as part of a mining risk assessment, which looks at the desk-based information and the available GI and records to understand what the risk of mine workings beneath the site comprise. Following on from that mining risk assessment, then we normally do a ground investigation where we do intrusive works to understand what depth workings may be present at, whether there has been workings or not, so that we can essentially truth that risk assessment and better understand what the mining risk beneath the site might be. That's then written up into a GIR, which is a ground interpretive report as part of GRIP 4. And then following on from that site investigation in line with our mining risk assessment, we determine what the mining risk mitigation remit is, which is essentially what mining mitigation we're looking to do on the site. It's also worth at this point just mentioning about coal mining, coal authority permits. The permits are required for any intrusive works that involve interaction with the coal seam. They are issued by the Coal Authority, Mining Remediation Authority, and they, I said, are applied for when we're doing any ground investigation works, any construction works that interface with a coal seam, or any probing and grouting works or remediation works, such as what we're going to be talking about through today's presentation. Thanks, Alex. So in terms of the mine working at Hill House and what we've known from desk-based assessment before we've started on the site, the top right image there is taken from the Abandoned Mine Workings Manual, which just shows where evidence of coal mining has taken place within the UK. That's obviously the SNP for the area that is most relevant to what we're talking about. And it shows there's been significant coal mining working undertaking within the footprint of TRU. That's due to the site being underlain by the Pennine Lower Coal Measures, which has a number of different coal seams present within it. The image on the left-hand side there is the geological map for the site. So you can see Hill House is in the little red shape in the middle of there. And you can also see there's some solid dark lines there, which correspond to where the coal seams outcrop. So within the Hill House area, we've got 3 particular seams that are of interest. The HB represents the hard bed seam, which has been extensively worked across the area, and that's the most shallow of the seams underneath Hill House. Underneath that then is what's known as the middle band coal seam, which is a thinner seam with not as much anecdotal evidence of having been worked, but beneath that again is the soft bed seam. So beneath Hill House, we do have 3 sort of coal seams that run one beneath each other. And as I said, there has been evidence of those seams being worked in this location. If you can go to the next slide, Alex. This is one of the abandonment plans that just shows what that workings look like. So again, the red outline is the Hill House site. What you can see on the left-hand side in the kind of orangey colour is workings of the soft bed seam, which is the lower of the seams that I've just mentioned. And you can see there the kind of roadways that have been worked and the extent of extraction of coal beneath the site. That was undertaken in sort of the mid-19th century in that area, I said, as shown in the orange. The pink section then is working of the hard bed seam, which is the most shallow of the 3 seams beneath the site, and that was undertaken at the turn of the 20th century. And again, you can see the areas where the coal has been extracted through the kind of squares and rectangles of shapes there, which just shows where working has taken place. So we know beneath the Hill House site, there's been quite significant evidence of working of both coal seams that are of particular relevance. If you can go to the next slide then, Alex, please. So what we've done is essentially gone through all of the desk-based information as part of our mining risk assessment, and that just allows us to get a kind of understanding of what risks we may need to consider and what investigation work needs to be done. So this just summarises the last abandonment plan plus some other sources of information, just to show the kind of extent of working that we have beneath the site. So the orange and the pink sections are from the previous plan. So they're called in to show that area. We've also had evidence that there's been part of the site that was purchased for mineral extraction, which is a sort of upside down grey L that's in the middle of the site there. So again, expecting there could be workings and extraction of materials from here. Evidence of old coal hollows where the coal has been worked out. So it's quite a complicated site in terms of coal mining, and therefore what the risk beneath the site is for any works that we do. If you can get to the next slide, thanks, Alex. This is our cross-section that we produced on the basis of the ground investigation works that we then specified. So here you can see the three darker lines running sort of left to right across the site. These are the three coal seams that we've been talking about previously. So this cross-section is taking the south of the site on the left, running to the north of the site on the right there. So we've got evidence from here through the GI that's been undertaken. There's evidence of voiding. That voiding is sort of metre and a half in thickness, sometimes greater than that. And that's picked up the location of where the hard bed seam is, the middle band seam, and we know that the soft bed runs underneath that, and that's been picked up in one of the deeper boreholes that was undertaken on the site. What we've also got evidence of here, which ties into what our risk assessment has showed us, is there's evidence that there's actually been some shallow working as well. So not just the deeper working down to the level of the coal, but also extraction from ground surface. And the area sort of pink at the top left there shows us where the made ground is, i.e. that the material has been excavated out to access the coal and then been replaced back. The scale on this on the in the y-axis, sorry, is that the bars are 20 meters in depth. So we've got a situation on the very north of the site where the hard bed coal is about 20 meters below ground surface, and the soft bed is sort of 40 meters below ground surface and falls away. So from this, I say we can understand a little bit more about where the coal seams are and obviously how they influence our site. The other thing that we've shown on this figure, then, just to provide a bit of context, is something that's referred to as sort of the rock cover above any workings. So the Syria guidance recommends that to mitigate against any mining collapse, we should be looking at having a thickness of rock of around 10 times the seam thickness, so what's known as 10T. And typically, if we're in areas where we have more than 10T rock cover, that means that should there be any collapse of workings, that doesn't normally propagate to the surface. Again, as you can see here, this is what the lighter grey band is showing, is essentially 10T rock cover above any working. So anywhere where the dark line is above, or sorry, intersects with that light grey colour, is where we think there could be a risk from mine working collapse beneath the site. Thanks, Alex. The other thing that our mining risk assessment has been able to identify for us is the presence of mine shafts in the Hill House area. So this figure just shows the different mine shafts that are present within the locale of the site, some of which are within the site boundary and some of which are outside of it. And as mentioned earlier, these are likely to target the deeper workings beneath the site, the ones that are about 40 meters or so below current surface level. So what we've got in particular interest here is shaft A, which is the one on the right-hand side within the sort of red boundary. which has been picked up from historical information and records. This one is in a vicinity of where there was an old engine shed, and there's records from the 1920s that this one did collapse and was repaired and was capped again. On the left-hand side then, the two sort of slightly larger red circles, shaft B and shaft AS1, these are mine shafts that have been identified as being within the footprint of the site. And we'll talk about those in a little bit more detail later, because we did do some investigation works to try and identify the locations of those. Thanks, Alex. In terms of then determining what the mining risk mitigation is, so i.e. what mitigation we may need to take from a mining perspective, we consider a number of different factors to help us inform what the risk of mine working collapse is and what the consequences of any collapse would be. So when we're talking about mining collapse, we're talking about what's shown essentially in that figure in the bottom of the slide there, whereby the roof of any working collapses in, and that collapse essentially propagates up through the ground so that you notice it at ground surface. So that can either be as a crown hole, so as a sort of a reasonably small diameter surface depression, or it can be slightly larger in size depending on what the ground conditions are like. But when we're talking about this now in terms of the mine working mitigation, this is the kind of thing we're looking to understand and assess whether or not we need to do treatment against. So whether or not we do need to do that treatment is based on a number of things around the probability of this collapse mechanism actually happening. So one of the key criteria is obviously the thickness of the rock cover above where the workings are. So the greater the amount of rock cover that you do have, the less likely that collapse propagating to surface would be. And as I said, 10T is the recommended thickness. Then we're also looking for the presence of any voids during the GI that we do. So again, you can have coal seams, but if they've not been worked, they're not presenting a risk of collapse. In areas of the rail corridor where there are existing tracks, we can look at whether or not there are any track defects. So any evidence of track movement, which might indicate that the ground is moving. Also looking at actually what we're proposing to do with the works. Are we proposing to change any of the loading or any of the stress conditions on the ground? So the ground is experiencing something different, which may then lead to the potential for any collapse. And also what construction techniques we're using. So are we, for example, introducing vibration into the ground that might lead to sort of some of the roof of these workings collapsing in? That's also considered then alongside what the failure of the consequences of any failure might be. Obviously, the number one consideration is safety and ensuring that everybody who is using or in proximity to any of the works is appropriately considered. There's the cost to undertake any repairs or mitigation that might need to happen following a failure. There's the impact on service, so how the rail network is impacted, should there be any mine working collapse, and also obviously the reputational issue of depending on what particular mechanism and what particular impact is affected. So those kind of criteria in terms of what the probability of failure are, and then therefore what the consequence of any failure might look like, is what we use to then be able to determine which parts of the site need any mine working mitigation. If you can go to the next slide, please, Alex. So what we've done on the Hill House site is go through each of the different parts of the new infrastructure and assess each of these as to the points that I mentioned previously, and therefore whether or not any mine working treatment is required. And obviously this isn't just done by ourselves as designers in isolation, it's also done in consultation with Network Rail as well. So on Hill House, there are a number of different features that we've looked at. So the green top right is a new retaining structure that was needed to essentially allow the length of the sidings that was required. The yellow colour is the access road, the dark blue is the tracks themselves, the pink square is the new TOC facility, and then the light blue is a siding associated with access to the main line up at Red Dolls. So having gone through that process, we've concluded that there were some areas of the site that did need treatment, and there were some areas of the site that we weren't proposing to treat. So if you can go to the next slide, please, Alex. Thank you. So one of the areas that we did determine that we needed to do mine working treatment was for the new retaining wall that we were building. This was on the basis that it was new build construction. It's a quite significant board pile wall, so 4 meters retained height at its greatest, but also supporting a slope. And on the top of that slope, then there's residential properties. So in this instance, the risk would be that if there was any collapse of any material into the worked hard bed seam beneath the site, that could propagate up and loosen the support of the retaining wall. And therefore that could have a significant impact in terms of failure of that retaining wall and therefore safety and cost implications to remediate. So on that basis, we determined for the retaining wall that we did need to do some mine working treatment. Yeah, the next slide, please, Alex. Thank you. However, as an example of where we haven't undertaken treatment at Hill House, we didn't propose and undertake any treatment under the new tracks themselves. This was on the basis that the site had previously been used as stabling facilities. There's evidence that tracks have run in that area previously. Given what we know the ground conditions to be, if there was any collapsing of the roof as per the sort of image on the right there, that's likely to result in some collapse of the rock head, but ultimately that would be identified as a depression at the ground surface rather than any kind of significant ground collapse because of the thickness of made ground that we have. The other factor then in association with this in terms of a safety perspective is obviously we in a depot are running at low line speeds. So if there was any collapse that occurred, it should be visible given the depression at the ground surface, and the trains wouldn't be running at speeds that wouldn't be able to appropriately accommodate that. So as I mentioned, the area that we did determine on the Hill House site we needed to do some mine working remediation was beneath the new retaining wall. The proposals and the process of doing that treatment involves drilling a number of holes to where the voiding is, and then essentially filling those holes up with grout. And if there is voiding present, then there'll be a significant grout take, and as a result of that, you can essentially fill the voids with grout and prevent any collapse from occurring subsequently. That's done usually through a grid arrangement of drill holes. So the image on the right there is just giving a schematic of that. Typically, there's a series of preliminary holes undertaken about 18-meter spacings, and those drill down to the working level, the level of the working, sorry. They fill up the workings with grout, and if you get a significant grout take, you know that you have voiding present. If you do then have voiding, you progress to a 6-meter grid, which is primary infill of holes, and then again, if there's any further grout take in those, you reduce the grid spacing down to secondary and even tertiary holes. So what you're looking to do is if there are any voiding, as per the image on the left, any space, any voids that have been created through mine working at seam level, you're filling those holes up with grout to protect any collapse from happening. What we did have with the retaining wall is that we did have a slope that was existing on the site, which we had to accommodate. So we did have a series of incline drill holes there, which allowed us to undertake the investigation, the grouting, the probing and the grouting, and adequately fill the void in. And Alex and Anjana will talk through that in a little bit more detail later in the presentation. So in terms of what this looks like on plan, it's a series of holes essentially that are advanced. This pink extent there covers the extent of the retaining wall, which you can see in the back image there. And what that does is, as I said, the yellow holes will all be undertaken first, and then they'll advance through to the red and the blue holes to ensure that everything is adequately investigated. And you can see at the top of the image there, the hole spacings is a lot closer, and that's just because of the angled nature of holes beneath the existing slope. Very quickly then, just to provide a bit of context on the mine entries as well, which I did mention earlier, there were the 2 mine entries beneath the site that we identified from the mining risk assessment. And obviously the risk with any mine entry collapse is that you notice this as a significant crater at the surface, because obviously the depth of the hole and the material being lost into it. We did have a situation where, because of the Hill House site being quite constrained, we did have the reception road running very close to these mine entry locations. And so we did need to actually identify where those shafts were, or at least confirm that their locations were not going to impact the permanent work proposals. Typically, to investigate mine shaft entries, you would follow a sort of spiral of drill holes, which is the image on the bottom there, where you start with the location that you believe the shaft to be in, and you spiral out until you eventually identify where the mine shaft is located. Unfortunately, in the case of Hill House, if you can go to the next slide, Alex, it was made slightly more complicated by the presence of a grade 2 listed coal drop structure, which is the photo top right. And you can see that then also bottom right, the top of it, it's a brick and timber structure that was constructed to facilitate coal movement from the sidings to the wider Huddersfield area. That coal drop structure, due to its listing, did come with exclusion zones from both a planning and a design perspective. And so we had to make sure all of our mine shaft investigation works were situated outside of the exclusion zone at the back of the coal drops. And we ended up proposing, therefore, a series of inclined drill holes, which allowed us to better understand the location of where the mine shafts would be. So the image on the left there, you can see the sort of darker purple colour is where we believed the shaft was from the desk-based review that we did in our mine working risk assessment. And then from there, we've got a zone of uncertainty associated with that. And we've carried out a series of drill holes, which allows us to confirm whether the shaft is present in that area or not. Thanks, Alex. And just very briefly, this is what it essentially looks like on plan. So you can see there we've got two grids, or 2 arrays of holes that are being drilled on the site. It's something like 250 holes that were drilled per grid to work consensually from outside away from where the shaft is, and then kind of work its way forward towards the shaft location to essentially disprove the location of the shaft beneath the site, such that we knew it wasn't going to impact the permanent works proposals. And then just to add in a little bit more complexity into our mine shaft investigation, we did also receive some survey information that was eventually undertaken on a deep sewer that ran beneath the site, which located it actually not where we thought it was, running sort of further north, but running directly through one of our arrays of drill holes to identify where the shaft location was. So you can see in the image on the left there, what we've had to do is an assessment of which of the proposed drill holes was going to then clash with the deep sewer, obviously needing to avoid impacting that during the investigation works. And then subsequently, the image on the right is to completely redefine where the arrays are, so that we're doing the investigation that we need to do without impacting the works underneath the site. That's a little bit of context on the design. I'll hand over to Alex and Anjana now to talk through the site works.
That's great. Thank you, Claire. Yeah, so like Claire said, myself and Anjana are now going to talk through some of the practicalities of taking this into the site works. We've been working here at TRU for a couple of years now, collaboratively with colleagues in BAM Nuttall and with site support from Arup. So now I'll hand over to Anjana, who'll talk to you a little bit about how we drill holes.
Okay, Alex. To carry out drilling works, we use hydraulic drill rigs with a rotary top hammer. The image on this slide shows a Casa Grande C6 drill rig drilling in hill house. We can also see that excavator with manipulator in it, which is used to pull roads and casings. A normal drill crew includes one driller, one excavator operator, and an assistant driller. All drilling works are supervised by a drilling supervisor or a lead driller at all times. In many cases, as mentioned, the surface area is smaller than the treatment area required by the design. Where possible, we drill it vertically to intersect the coal workings. If the treatment area extends beyond the working area, then we drill it inclined. At Hill House, for example, drilling angles range from 30.7 degrees to like vertical to 30.7 degrees, but the rigs can drill up to 40 degrees inclined. Before starting drilling, a temporary drilling platform is set up for the rig. That's in Hill House, but for other sites where we are drilling on track, we use bog mats for stability, more stability. Once the borehole location is marked on the platform, the rig is tracked over to the location and we set up the rig according to the inclination and bearing. So after the rig is set up on a particular location, we case it into the superficial till the casing reaches a bedrock. The casing has a casing shoe that cuts through the soil, and which is the soil, the debris is cleared by water, flesh, and driven into the casing is driven into the bedrock. We use casings with diameters of 88.9, 101, and 133 mils, depending on what type of hole we are drilling. As mentioned earlier, we drill infills, perimeters, and preliminary boreholes. They are of different sizes. The casing will be different for each of them. Once the casing is in place, we then drill it with a T38 steel rod, which has a button bit in it, which is 76 mil or 101 mil, depending on the type of borehole we are drilling. The boreholes extend 2 meters below seam level or deeper if the coal or workings are not encountered, typically to around 20 meters. To keep the borehole open, once the casing is removed, we install sacrificial PVC pipes. The PVC pipe has slots at the seam level for grout injection. At sensitive sites like Huddersfield Station, we confirm the PVC duct counteracts active earth pressures to prevent collapse between disruptive positions. The key health and safety measures that's included while drilling, we use an excavator with a manipulator to handle casing, and so that reduce manual handling. We also comply with coal authority permit by using gas monitoring, using 5 gas monitors to monitor the gas levels throughout the work. And instead of using a normal air flush, we use a water flush to remediate any other problems. So we also create restricted zones using barriers and signage to isolate the drilling works from other teams working in the area. Next slide, please.
So I won't dwell on this slide for too long. Hopefully this video will work. Looks like it is working. So for some boreholes, when we encounter the workings, it's then part of the specification to inspect some of the workings with a camera. So utilize the kind of type of camera you'd use for like a drainage survey. If I just skip ahead a little bit, borehole, and then at this point here, so then this is essentially what we're drilling down to find and treat. Looks like almost the borehole's gone down through a coal pillar that's still intact, but that's right next to some open workings. And coincidentally, this video was taken 2 years ago to the date. I won't play the whole thing because I think that shows it pretty well. How do I move on? There we go. Back to you, Anjana. You're on mute.
Sorry. Working in shallow coal mining areas presents several risks that include ground stability. While we are drilling, we sometimes encounter some unusual voids that are like greater than 2 meters, which stops our works, and then we create an exclusion zone. Then, as shown earlier, we do a scan probe survey to make sure the void that we encountered is not that big, or like what's actually inside the borehole, that we make sure it's okay and then carry on drilling. Otherwise, we set up an exclusion zone around it. Also, there will be issues with ground gases since it's a coal mine. So gas levels are monitored throughout drilling. If gas levels exceed limits, all work ceases, and we wait till it's gone off. We normally wait it for 15 minutes, and if it's not, then again sort it out. Combustion risk. Exposed coal can ignite, so we use water flash instead of air, as mentioned earlier. So all the water, also the contaminated groundwater risk, all the water that we are using on site is treated using a siltbuster before discharging. So working is risky near a shallow mine shaft or mine workings. There is an but a video of a rig working near a mine shaft and what actually happened. You can see the rig in that video.
So
there.
not one of our sites we should also make
Yeah,
absolutely clear.
that's not a TRU or a BAM site. That's in 2012. Actually, you can see the rig working in near a shaft, so it just went into it. Luckily, nobody was injured or anything. A resident was close by who saw the driller buckled into it, so he just helped him escape. So nobody was injured, but this can happen. So it's essential to keep a safe system of work and exclusion zones around wherever we are working. Yeah.
Incredible.
Yes. So when investigating mine entries in Hill House, we implemented a structured safe system of work where exclusion zones are established around the mine shafts, zone of influence, and reduced gradually if no shaft is found. As mentioned earlier, there was a coal drop structure nearby, so we monitored the vibration levels using a V900 seismograph to ensure no structures nearby are affected by our drilling works. We also use total stations to measure or monitor the subsidence. While drilling, we used a fault arrest system with a rotor telehandler with spreaded beam, as you can see in that picture. When we are like working in restricted areas, we use that kind of setup. If unexpected features are encountered like the ones we encountered in E13 forecourt and flyover site, that's not Hill House, but another TRU mining site. If we encounter such an unusual void or something, then we move the rigs away safely away from that feature, and we do a camera survey. We don't normally do it by walking into it, but we normally do it by with the help of a mute, and then after checking it, we then grout it. That's also outside the exclusion zone with a mute. So if the grouting is like around 1.5 cubic meters, then we'll consider it as normal because that's the grout levels that we are seeing throughout TRU. But if it's something like 30 cubic meters, then more action will be required from our side. So yeah, that's how we deal with it.
Thanks, Anjana. So now I'm going to talk a bit about the actual grouting of the drilling and grouting mine infill projects. So this photo here is an old one from a site I worked on a good few years ago. I just wanted to bring this up as some kind of context of how of how bad these sites can look in practice. But thankfully, this is not a BAM site or a TRU site. So for the contrast, this was the grouting setup we used at Hill House. So the actual mixer is there in the middle. The green thing, that's an 8-cube mixer with an agitator. So whereas in the previous photo, the kind of fly ash was just tipped on the side. We typically use where we have the space silos to feed the grout mixer. So there's 2 fly ash silos there and a cement silo. So for quality control, as we're working, we can take wet grout testing. So mud balance to check the density is there or thereabouts of where it should be. Use a flow meter to check the workability and the pumpability of the grout, and bleed tests to make sure that the material isn't separating excessively and is in within the requirements of the specification. I'll also take cube samples to be crushed, and that's just to ensure that the compressive strength of the grout is in line with the specification as well. So during the mixing, we'll monitor the flow and the volume of grout that we're pumping. So typically you'll have an operative stationed at a flow meter, and then another operative at the borehole itself, communicating with each other through radios. And then the grout is injected into the borehole just quite simply under gravity feed with a tremie to get it to the bottom to be targeting the work levels. So some of the health and safety considerations to take into account with mixing grout. Quite a big one is obviously dust. So both PFA and cement, when you're working with it, brings quite a lot of dust into the atmosphere. So this setup we had here is almost zero dust. And then operatives would also be wearing positive pressure, RPE, in and around the mixer. And then fast forward into one of our current sites. This is the Ravensthorpe flyover area where we have a slightly different setup. So we didn't quite have space to use the silos, and access was a bit more difficult to get deliveries to the silos. So here we had to use bagged PFA, and so then you introduce the risk of you essentially have to lift the bags with an excavator. So you had this you can see here this stand fabricated and designed to mitigate the risk of people being near or under suspended loads, and also here bagged cement on a pallet lifter to then reduce the amount of the distance you're lifting the bags of cement into the mixture. Carry on. So one of the main constituents of the grout we use is pulverized fuel ash, or PFA for short, also known as fly ash. So we use this either in a 10-to-1 PFA to cement or 5-to-1 PFA to cement mixture, depending on whether it's a perimeter or an infill hole. Now this is produced as a byproduct of coal-fired power stations, and it's historically used because of how readily available it would be, with a lot of historically a lot of coal-fired power stations around, and it also has some properties that make it particularly good for bulking out the grout. It's pozzolanic, so when it's mixed with cement and water, it essentially gains some cementitious properties, and then it self hardens to make a cement-like material. So that, coupled with it being historically readily available and historically relatively cheap, it made it the perfect material to be mixing and pumping in bulk on sites. However, since closure of all the UK power stations, it's more difficult to get your hands on. It typically comes from abroad, but still just about cost effective and kind of carbon efficient compared to cement on its own, given the quantities that we use. Back to you, Anjana.
After completing all the drilling and grouting works, we do the validation testing. This is according to the specification that we do. For validation testing, like drilling a normal borehole, we drill a borehole, we case it to the bedrock, then we drill it with roads to the target same level. Borehole is then filled with grout under gravity feed until the grout reaches the surface, and then a T-piece, as you can see in this video. If you can play it, Alex. Sorry. A T-piece is then put on top of the borehole to measure the pressure. The test ensures the borehole holds 0.1 bar per meter of overburden for 2 minutes. So it should hold the pressure for 2 minutes. That's how we validate the area that we drilled and grouted for mine and fill works. Yeah. All the data is collected digitally. We use BIM to record drill and grout logs. The operators record it in their BIM 360 templates, and then engineers check and export it to our master Excel data sheet, which is stored on our SharePoint. You can see the BIM logs in that screenshot earlier, and our tracker, which is used to identify which ones we drilled, which ones is already grouted in. That helps us analyze the area better. The data capture tools we implemented played a crucial role in projects with tight deadlines, particularly in Huddersfield Station and Wall 23 sites, providing real-time access to all parties, including the not just internal PAM people, but to the designers as well. This helped accelerate project completion by 3 months, resulting in substantial cost savings of approximately 1.3 million. One of the major risks at the time was Huddersfield Station mine and fill, yet the early completion successfully mitigated this challenge. However, moreover, it allowed for the early commencement of enabling works for the station canopy replacement, further streamlining the project. That's me.
Cool. Thank you, Anjana. So here's a bit of a summary of all the projects we've worked on to date at TRU. So we're currently working at the Ravensthorpe flyover, which is a new flyover structure. Also working at the Baker Viaduct, which is just a little bit east from the flyover, and soon to start the Ravensthorpe Station footbridge works on disruptive possessions that are coming up in about a month's time. So yeah, some fairly big numbers there that we've pumped. So all in all, about 2.2 million litres of grout have been pumped into mine workings, and a meterage of almost 55 kilometres, which is the total number of boreholes we've drilled. And And then on to conclusions. Do you want to talk through the conclusions, Claire? You put this slide in.
Yep, I'm happy to do that. So I guess just to summarize, obviously, we've just given you a bit of a flavor around mine working risk, how we go about assessing it, what the site works in terms of probing and grouting look like, and obviously what that's meant for the whole of the TRU site to date. And in terms of Hill House specifically, we've gone through an approach to manage the legacy mine workings under the Hill House site, which were reasonably substantial. We've completed all of the grouting works beneath the retaining wall. So those 3 photos on the side there is the grouting works actually occurring. The middle photo is you can just about see the piles that have gone in for the wall, and then obviously the bottom photo there is the piled wall itself. We've completed the mine entry investigations and have demonstrated that within the zone of influence to the permanent works on the site, the mine shafts weren't present. And that work has actually been recognised as a finalist within the Ground Engineering Awards last year. All of the works that we've talked through, both in terms of the retaining wall mitigation and the mine shaft investigation, has been undertaken using appropriate safe systems of work, which is really important, as you've seen from the video of the rig collapsing into the hole. And then just to summarise that largely the construction of the permanent works at Hill House are completed. It's final, the final bits are being worked on now. And if you can go to the next slide, Alex. That's what the site currently looks like at this point in time. I suppose on behalf of all of us, thank you for listening, and we're very happy to take any questions.
Thank you. Yes, that was excellent. That was a really interesting presentation. We have got a couple of questions in the chat there. If I'll just run through them. So the first one from Richard Hellings. What's the significance of the red and black coloured borehole marks on the plan? I think I made a note. I think that was in relation to something on slide 13 that you have.
In terms of the for the mine shafts, is that, sorry? I'm just trying to remember which one slide 13 would be. This one?
Yes, I think it was that one.
Yeah.
Sorry, I think it was the one with the.
Oh, was it the one before it? Right, sorry, Rick.
Yeah, the old plan on it. I think it just had some records of boreholes on it. Might be the next slide down.
This one?
Yes, that's it. Yeah. So you got some markings with a black icon and some with a red.
Right. Yes.
There's the 2 different colours there. So the red is the red line boundary for the site. That's what the red line around the external is. The black is just denoting where the extents of the coal hollows are. The pinky colour is, as I said, is the working of the hard.
Sorry, on the actual little boreholes themselves, they're like little circular icons.
It's just phasing of the GI. So the black ones were previous ones, and the red ones were ones that were being proposed. Sorry.
Okay, that's okay.
Okay. You've also got another question then, Rick, as well. So is the scaling of the 10T ratio based upon the depth of the seam? I'm not sure if you covered that, did you? Because you would expect the risk to be lower if the seam was of a greater depth. Yeah.
So the T in the 10T assessment is based on the thickness of the workings. So typically, obviously, when coal has been worked, the thickness of the workings itself is normally such that it allows, obviously, person access into it. For the purposes of assessments, this is taken between sort of 1.5 and 2 meters as typical sort of roadway walk, so that a person could walk down and coal could be extracted on. But you're completely right. I mean, 10T is the sort of empirical value that's considered in terms of where you get sufficient bulking of any rock collapse to mean that you don't notice any depression at surface. But the more the number is in front of the T, so the closer to 10 you get, the more the risk is mitigated.
There's a question from Ed Edmondson. If plastic casing was used, was the treatment hole pressurized?
So we drill using a steel casing, and then the plastic casing is to keep the hole open once we've pulled the steel casing. And so it's fed in under gravity, so initially not pressurized, but then, as Anjana covered, we undertake validation testing once all the infill holes have been completed, and then they are pressurized at the surface. But you'd also have to consider the so even in feeding it in under gravity, you have the pressure of the weight of the grout itself. So if you've got, let's say, a 20-meter hole, that can even, it does add up to a couple of bar of pressure of injection at the level of the workings.
Joe Flakes asks, did mine gas to off-site receptors have to be considered?
During the works? So I think as part of the permit application, that does get considered. You can jump in if I'm wrong there, Claire, but for our actual site works, the permit conditions are just to monitor at the surface of the borehole.
Yeah, the ground investigation does undertake ground gas monitoring as well, so we can understand whether there are gas emissions coming off the mine workings, and there is a ground gas assessment from a mine workings perspective for mine working gas. So we have an indication from the ground gas monitoring about whether or not we'd be expecting ground gas to be, released and emitted as part of any works that we do. Equally, alongside that, as I said, the permit does put requirements on us for ground gas monitoring, and there are also monitoring holes that are surrounding the works that are being done. So for the retaining wall, we did have a series of boreholes around the perimeter of those works, of which we were monitoring for ground gas, because obviously, particularly being so close to a residential area, we're wanting to ensure we're not, essentially pushing ground gas from the mine workings outside the site boundary when we're filling workings with grout.
Okay, excellent. Well, thank you very much. That was really interesting. I mean, I've certainly, a lot of that was new to me. That's not something I'm very familiar with. So yeah, very good presentation. Thank you. So if those that are still on, if we could give our appreciation in the usual way, whether showing of hands or if you want to applaud, take yourself off mute and applaud, then feel free. So thank you guys for that presentation. Just to remind everybody, yes, we have a seminar. So I'm going to say it